Hi everyone. Can you hear me? Can we do the same drill as yesterday? Please come online on video. 1 second. Okay. Let me see. All right, I guess I guess we can get started. Give me a second. I need to find a plug for my tablet. It just has half of the juice right now. Okay, that should be good. All right. Hi again, everyone. So let's continue where we left off yesterday. So we were talking about universality, and we defined it essentially in terms of consistency, and in particular, in terms of some generic notion of distance. Let me see. Yeah, some generic notion of distance. And we say that consistency just means this, right? It just means that the probability that we are approximately correct goes to 1, okay? For any epsilon. Before I proceed, I'll try to see if you guys have questions. Then we say that we have universal consistency for a given quote unquote universe, which here will make it simple. It just would be a set of functions, a function class, but a set of functions that we believe is very large, right? So for instance, all continuous functions, all Lipschitz functions, all polynomial functions of a particular degree. Usually we want the set of functions to be as large as possible, okay? And then ask, is our particular algorithm, f hat, consistent with respect to every single function in that large set of functions? Okay. Any question there? Then we started talking about nearest neighbor regression, and nearest neighbor regression is defined very simply. You just say the regression value that you're going to return is just the average y value of the nearest neighbors of the point x. Fine. And then we said at a high level that this is consistent. Okay, that this is consistent. I'll give you a couple theorems on consistency of this thing in a minute. And that this is not only consistent, it's universally consistent. But before we proceed, I wanted to give some intuition as to how this procedure behaves. And so the intuition we gave last time was, okay, we thought about the choice of k, right? And we say, let's imagine that k is very large. Then this is not good. F hat k would be just some constant. It's not a bad choice. If k is too small, again, it's not a good choice, right? Somehow we're feeding just noise. So in general, we want to choose a middle value of k, some type of middle value of k. And then the point is, how should that choice be made, right? And for what type of choice of k do we have consistency? So when we say k nearest neighbor is consistent, we don't mean for all choices of k. We mean for adequately chosen k. Immediately, we see here that a particular choice of k doesn't work. K and n cannot be consistent for that choice of k. If we always choose k to be equal to n, the sample size, we know it will not work. Why? Because we always just feeding a constant. It cannot be consistent in that case. Make sense? If we choose always K to be 1, it cannot work either because we always just feeding noise. It cannot be consistent to a large class. Okay? Any question here? Is everybody here? I need to hear somebody's voice because otherwise I feel like, okay.
Yeah.
Thank you. So, okay. So now let's think about something, okay? What is the intuition behind nearest neighbor method? The intuition is that the function f, why are we using the nearest neighbors? We're using them because we're saying that the function f somehow doesn't change too much locally. We hope that the function doesn't change too much locally. That's why we're using the y values of the nearest neighbors to infer the y value at x. Does that make sense? Okay. So let me write that intuition here. In the vicinity of any given x. Okay, so that's sort of the hope. And if that thing is true, then hopefully k-nearest neighbor regression works well, right? So the key point here is in the vicinity of x. So there is a question immediately, if I choose k in a particular way, how far is the kth nearest neighbor from x? Am I in the vicinity of x? So for what choice of k, are we in the vicinity of x? So let me define a particular quantity that will keep coming up. The nearest neighbor radius, I'll just call it the KNN radius. And I'm going to call it r hat k of x, which is the distance from x to the kth nearest neighbor. Okay. So to illustrate, if this is x, if this is my data point, so here we're in R2. If these are my data points, let's say that k is equal to 2, then this here is R2, R hat 2 of x. Okay. If k were equal to 3, then we need to go all the way here to r hat 3 of x. Okay. Fine. So the question for us is, how small is r hat k of x? Okay. Because note all KNN of x belong to the ball bx r hat k of x. This is that ball here. okay? Fine. And that ball becomes that neighborhood of X, the vicinity of X. All right. Now, there is a small little thing that I didn't say and nobody brought up, which is we could in fact have ties, right? In the distances. If two data points fall on top of each other, for instance, we have ties. Okay, fine. Or if in fact there is a third point here, then R hat 2 and R hat 3 are the same. Okay, but we're just going to, without loss of generality, assume that you break up the ties. However, if there are two, you can view, if there is another point here, you can view either this one or this one as the second nearest neighbor. Doesn't matter. Okay. So, all right. So we have this RK of X and R hat K of X. And the first thing to notice is that R hat K of X is a random quantity. Okay. And what we hope is that R hat K of X is small. Fine. If it's not small, then we are not in good shape, right? Okay. Now, notice this. What is the effect of the sample size on R hat K of X? Suppose I fix K to 2. Okay, I'm just looking for the two nearest neighbor. Okay. Let's imagine now that I increase the sample size. I have a lot more samples. Then clearly, R hat 2 of X should be what? Should it go down or should it go up if I increase the sample size?
Should it go down?
Is it a question or is it an answer?
I guess it will be more of an answer. It should go down.
It should go down, right? That's what we expect. We expect it to go down. Okay. If I have a lot more samples, then it should be likely that it goes down. Fine. But it's not guaranteed that it goes down, right? Because that's the point of randomness. It's random. Fine. But it should be likely that it goes down if I have a lot more samples, because the samples should fill up the space a lot more. Okay. So we expect R hat K of X to go down as n goes to infinity. Okay. And we'll show that this is indeed the case. Okay. So that's what we expect. And in other words, as the sample size gets larger, we should be able to pick larger K, larger values of K. Does that make sense to everybody? Okay. As the sample size goes larger, we should be able to pick larger values of K, because the larger values of K allows us to have less variability. We fit the noise less. Okay. And now with larger sample size, R hat K also gets small. So we are only using a point in a neighborhood of X. Okay. So let me write that down. For larger n, we should be able to pick K as a function of n larger. Okay. Now, having that intuition, I'll give you the main consistency theorem, one main consistency theorem. There are many different consistency theorems. Okay. The notion of consistency I gave you guys yesterday is probably the easiest notion of consistency. There are other notions of consistency, but in particular, the notion of consistency I gave was just under any distance, was under some generic distance between the functions. Okay. And so if you change the distance, you change the notion of consistency. But there are, in fact, various ways we can talk about a random variable, a random sequence converging to some other, to some point. Okay. There are different notions of convergence. This is the simplest notion of convergence. Okay. All right. Theorem. L2 universal consistency. So the assumptions are actually fairly simple. Let here, in fact, I'm just going to fix first, fix mu x. Okay, I'll fix the distribution of x. Fine. Okay. Let f denote the following class, all function f such that e of f squared of x less than infinity. Okay, where the e is taken under the distribution of x. Fine. Then you can imagine that this is indeed a very large class. It just says that the square of f is integrable, that the integral is finite. Okay. All right. So it's a very large class. Suppose that f is bounded, is upper bounded. Then this is immediately true. Everybody sees that. Suppose that f of x is always less than some constant, then that implies that this is true. Okay. So in fact, that means that I can have f non-continuous. It can be all weird as long as it's below some constant. It's sandwiched between some constant. Okay. Fine. So it's a fairly large class. All right. Now, then for all f in f, for all epsilon greater than 0, we have that the probability that ex of f hat k, where f hat k denotes the nearest neighbor classifier, KNN regressor, plutôt, nearest neighbor regressor, f of big X squared less than epsilon, this probability goes to 1. Okay. Where this is just our notion of distance between f hat and f, which we discussed last time. All right. So this is a very generic result. It says that the simple procedure approaches f, at least in this notion of distance, no matter what f is, as long as f satisfies this very general condition. Okay. Without knowing anything about f a priori. And don't forget, we do not know f in this distance, but this is true. Okay. Go ahead. There was a question. There was going to be a question.
Yeah, I was going to ask, what is fk in this?
F hat k is the class, the regressor we defined, the KNN regressor.
Oh, okay. Okay, cool. Thank you.
Okay. Fine with everybody? All right. So let's proceed. This is not very direct to prove. So I'll give you a simpler version of this theorem, a much easier fact to prove, and you get to see the intuition behind it. There is a big mistake I made in the statement of this theorem as I'm about to give the other fact. I just realized it. I didn't tell you for what choice of k, even though I just, the whole setup of discussing the choice of k was to set up this, this part, provided k goes to infinity and k over n goes to 0. Okay. So provided that as the sample size is growing, we're letting K grow, but we don't let it grow too fast. That's this part, K over N to 0. Okay, we let K grow, but we don't let it grow too fast. Make sense to everybody? Okay, so here is another version of the theorem. And here we'll just look at consistency at a point. And that one is easy to show, is much easier to show, and that's why we'll spend the time showing. Consistency at X, a fixed X in the support of mu X. So first, if you remember probability, what do we mean by support of mu X? Recall that mu X, we're letting mu X be the distribution of X. What is support of mu X here?
It's support of mu X where for any radius that's bigger than 0, there is a ball that's around X that includes the distribution or some of the points.
Yeah, that's it. Okay, so support of mu X is the set of point X such that for all r greater than 0, mu X of BXR is positive. Okay. It just says that X is a point such that in the vicinity of X, mu X has mass. Okay, the measure gives some mass, so it's likely to generate some point in the vicinity of X. That's all we mean. Okay. Fine with everyone? I'm going to erase this part. Fine. The definition of support. Okay.
So just a quick question. The support is different from inner points.
I cannot hear you. You have to speak up, please.
The support is different from inner points, right?
The support is different from what?
From inner points.
What do you mean inner point? To even talk about inner point, you have to have a set, and to talk about the inner point of that set.
Yeah, sure. Like if you understand distribution like a set.
The distribution is not to be understood as a set. The distribution is the set of, what is the distribution of X? It's the set of probabilities of event involving X. If I say, what is the likelihood that X is greater than something? It is determined by the distribution of X. Does that make sense?
Yeah.
It's the probability distribution from which we are drawing X. Easiest way to think about it is that population. It's the population from which we are drawing X. And it is the distribution of values in that population. Okay? Does that make sense?
Yeah.
Okay.
I just want to make sure, like, so for the support, it can be a circle of things in distribution.
Think about the support as where the distribution is non-zero.
Ah.
The support is all the set of points that are likely to be generated.
All right.
Okay, but we define it in the way I just defined it, because if I'm dealing with a continuous distribution, the probability that X is equal to little x is 0 for every X.
Yes.
Okay, so therefore we have to define support differently. We cannot just say that it is all the X's such as the probability is non-zero of generating X is non-zero. So we have to define it as all the X's such as the ball around X has mass. Okay. All right. These are the type of things that I want the TAs to also go back over with you guys. Okay. Any other question? All right. So consistency at X is in the support of mu X. And all we mean by it is that X is likely to have points around in its vicinity, okay, from the distribution. So consistency at X, again, under the same, suppose again that K goes to infinity, K over N goes to 0. Now let F be a simpler set. Let it be f, all the f such that f is continuous at x. You can see that this is still a very large set. It's a lot of different possible functions, okay? All the f such as f is continuous at x, then for all f in f, for all epsilon greater than 0, probability, now we just want to care about whether f hat k of little x approximates f of x less than epsilon. That probability goes to 1. And so this is a simpler consistency result. It just says consistency at a point x, right? We're viewing x as some future points, okay? That we would like to estimate f at.
I have a question.
Go ahead, please.
Yeah, does the second theorem, I mean the theorem at the bottom, does this theorem at the bottom somehow implies the theorem at the top, which is universal?
No, no, for a quick reason, right? Big F here is a much larger set than this set. Okay. Big F allows functions that are not continuous. Okay.
Okay.
All right. Okay. So I hope, yeah, the theorem should be clear, and we'll just try to show this. Let's start with some intuition. Let f hat k of x, we define it as 1 over k sum I in k and n of x, yi, okay? Where the yi, we view the yi as f of xi plus eta I, noise term. And we are also assuming that the eta i's are all independent from each other, okay? Fine. So I can rewrite this as 1 over k sum I in k and n of x, f of xi, okay, plus 1 over k sum I in k and n of x, eta I. And more importantly, we said E of eta I is 0. We view the noise as having mean 0. Fine? All right. So having written it this way, let me give a name to these things. I'm gonna let this guy, I'm gonna call it f tilde k of x. Okay. And this here is just f hat k of x minus f tilde k of x. Okay. So a first thing for intuition, let me draw out what we have here. So let's say that this is my unknown function. This is f, unknown. Let's say this is the query point x. These are some values on here. Actually, these are some values on here, on this function, corresponding to these samples. Let's say that this is r hat k of x. So these are all the nearest neighbors. Okay. What is this thing doing? It's just averaging these values. All right. So this itself is not necessarily close to f of x. This is f of x here. Okay. But if we average this out, if f is continuous and we average this out, we hope that the average is going to be close to this. And if r hat k of x is getting smaller and smaller, that average should get closer and closer to this. Make sense to everybody? Okay. So we hope this goes to this as n goes to infinity, and it's a question mark. Okay, we need to show that. All right. Now, let's think about this quantity. It is also an average, right? In fact, I can write it as eta bar. Okay. It is an average of independent eta i's. Okay. And the hope here is that since it's an average, the average hopefully goes to its mean. Agreed? And what is the mean? It's 0. So we hope that this goes to 0. Okay? Make sense to everybody? And so we just have to establish tools that allow us to say these type of things. Fine? Okay. This in particular what we have is that f hat k of x minus f of x is at most f hat k of x minus f tilde k of x plus f tilde k of x minus f of x. Everybody agrees? Right? What did I use? I just used a triangle inequality. Fine? Okay. A plus B is less than A plus B. Okay. Fine with everyone? Now, I'm going to call this, they call this a variance term. And they call this a bias term. If you study machine learning or statistics, these terms, variance, bias, decomposition, things like that will come up often. Because we tend to try to think about these questions. Are we approximating? Are we learning? We try to think about it in terms of terms like this. All right. A part that just fits the noise and a part that is trying to approximate the function without the noise. Okay. And the parts that fits the noise, we tend to call it the variance term. All right. So let me go back here. In fact, and I'm going to add a little something, a little assumption. It's a basic, very banal assumption, is that the variance of the noise is bounded. Okay. If the variance of the norm is of the noise is not bounded, it's hard to say anything. Okay. Fine with everybody so far? Now, so I'm gonna call this V of X plus B of X. V for variance, B for bias. Okay. Right. And what are we trying to show? We're trying to show that we're trying to understand in what situation is this thing less than epsilon. So it's enough to understand in what situation this term here is less than epsilon half, plus this one is also less than epsilon half. Okay. If I can say that as n goes to infinity, this is less than epsilon half, and that this is less than epsilon half, I'm done. Okay. Fine. In particular, I just have to bound away the probability that this is not less than epsilon half. If the probability that this is not less than epsilon half, and the probability that this is not less than epsilon half, if those two probabilities are small, then we should have consistency. Does that make sense? Okay. In other words, let me rewrite what I just said. We just need, we have already this fact that probability f hat k of x minus f of x less than epsilon, okay, that this probability is in fact greater than the probability that both v of x and b of x are both less than epsilon over 2. Okay, because if this is true, if both are less than epsilon over 2, then this is true. So this probability is larger. Okay. And then since this is on end, this is larger than the probability. This is larger than 1 minus the probability that v of x is greater. I just need the equal. Actually, it doesn't matter which direction I go, is greater or equal to epsilon over 2 plus the probability that b of x is greater or equal to epsilon over 2. Okay. So I can look at the two terms separately. Fine with everybody so far? Okay. So let's look at the variance term. The variance term is this term, f hat k of x minus f tilde k of x. Okay. And we are asking whether this is less than some epsilon over 2. All right, with some probability. Okay. For intuition, we already say that this is nothing else but 1 over k sum I in kn of x eta I. Okay, it's just a sample average. All right, so we're just asking whether the sample average is close to its mean. All right, fine. So for now, assume for now, this is for rigor's sake, assume for now that x1, x2 through xn are fixed. Okay, why do we want to assume that they are fixed? Because then truly this is just an average of IID, of independent terms. Okay, so I'm just going to use a conditional probability to start with. Fine? Fine with everyone? Okay. Note also the following. so just a quick remark that if x1 through xk are fixed, the expectation, conditional expectation, so of the yi's condition on xi's, the expectation of f hat k of x is really just f tilde k of x. Why? What is f hat k of x? It's 1 over k sum I in k and n of x, yi. Okay. If I take the expectation of this and I assume that the xi's are fixed, this sum is fixed. It's no longer a random sum. Okay. The k and n are not random. It's determined. So only the yi's are random. So in any case, I can pass the expectation inside. Okay. And the expectation of this is just f of xi. Okay. And 1 over k sum f of xi was exactly what we define as f tilde k of x. Going back to this picture. Okay. So all we are asking is this far from its expectation once we fix the xi's? Any question here so far? Fine with everybody so far?
I have a question. So if those x1 through xn are not fixed, so why are this not independent identical distributions?
Oh, I can, they are not, they don't have to be identical to start with, right? They don't have to be identically distributed.
Yes.
Right. Does that make sense?
Okay.
The eta i's don't have to be identically distributed. There could be a particular level of noise here and a different level of noise here, but they are independent. I generate the x, then the yi, then the eta I is generated independently. Fine.
All right. So
I can generate all the x's first, and then the eta here could have this variance. This one could have this variance. This one could have this variance. That doesn't matter. They are independent, but they don't have to be identically distributed.
Okay.
That's the first thing. Okay. The main reason why I'm fixing the x's first is that you'll see it in a second. Is that I want to talk about the probability over the entire sample, meaning over the yi's and the xi's. But first, I just want to talk about the probability over only the yi's, assuming that the x's were generated first. It simplifies things.
all right.
Because then I'm only talking about the noise. I'm not caring about where the x's are situated.
Okay. By the
Does
way,
that make sense?
what's the full name of IID?
Sorry,
What's the full name of IID?
is what?
When you mentioned IID, what's the full name of it?
Independent and identically distributed. Identically distributed means they have the same distribution.
All right. So you said they are IID, but not identical?
No, I'm saying the eta i's don't have to be identically distributed.
Okay. So
The
what
moment I
are-
fix
what
the
are
xi's,
what
the
are
moment I fix the xi's, they don't have to be identically distributed.
Yeah. So what are the IIDs here?
The okay, yi is IID.
Oh, okay.
Why is yi IID? Because I haven't told you what x is yet. So how am I generating y? How am I generating y1? Y1 is generated by first randomly picking x1, then picking eta, and adding that to f of x1. Because x1 could have been anything, the y's have the same distribution.
Okay.
But the moment I fix the value of x, I tell you x is 1, x1 is 1, x2 is 2, then the yi's don't have to be, then the eta i's don't have to have the same distribution necessarily.
I see. Thank you.
Okay.
Thank you.
All right. Okay, I need to remember where I was. 1 second. Okay, so this is what we're showing. We going to argue that some random variable is close to its expectation. Okay, that's really all we have to argue. But before we argue that, again, a bit of intuition. Why would we expect that this thing is not too large? We can think about the variance of this. Okay, we can first think about the variance of this. If the variance of it is not too large, then chances are, most of the time, this thing will be less than some epsilon. If the variance is very high, then maybe not. So first, we want to understand that the variance is small. Make sense to everybody? Okay, so again, still conditioning on this, let's look at the variance of 1 over k sum eta I in k and n of x. What is that variance?
It's the random variable minus the expectation squared.
Yeah, but now, okay, that is true. That is the definition of the variance. What I'm asking is, let's apply the definition. What do we get? So let's think about it for a second. The expectation is 0, right? And the eta i's are independent, right? So a first thing right away is that this, a rule of variance is that this is equal to the variance of eta I. 1 over k squared, sum of the variance of eta I. Agree? Okay. The sum of independent random variables, the variance of it is the sum of the variances. And so this is less than, how many values do we have here? We have k values, right? So this entire thing is less than sigma squared over k. Fine. So right away we see that if k goes to infinity, if k goes to infinity, then this variance goes to 0. Okay. Fine. Now let me. But what we are interested in is really the probability that this term, so the variance term, we call it v of x. What we really are interested in is that the probability that v of x is greater or equal to epsilon, that probability is small. Okay. Fine. Okay. So some basic tools. I'll call it some basic tail bounds. Okay. We call this type of thing a tail bound because it is the tail of a random variable. I'm looking at this as a random variable. And if I think of a random variable as having a distribution like this, and I'm asking what is the probability that the random variable is greater than epsilon, I'm looking at this part. It's the tail of the distribution. So it's called tail bound. Okay. Fine. I hope we are doing fine on time. Let's see. So basic tail bound. The most basic is called Markov Inequality. And it is possible that in the other courses that you guys take this week, these things might come back. Tail bounds are very important. They keep coming back. Okay. Every time you're dealing with probabilities, especially in engineering domains, such as computer science, you'll get, you'll have to go through tail bounds. Okay, so Markov's inequality just says this: let z greater than 0 be a random variable. Then probability that z is greater or equal to t is less than the expectation of z over t. Okay. And the proof, I'll just give you a very simple proof of it. T times the indicator that z is greater or equal to t. Everybody knows what an indicator is. It's that function that is 1 if its argument is true and 0 otherwise. Okay? If z is greater or equal to t, this whole thing is equal to 1. If z is not greater or equal to t, then this whole thing is equal to 0. Okay? Then this thing is less than z. Everybody agrees? Because if z is greater or equal to t, then by it's a tautology, z is greater than t. Okay, this is 1. If z is not greater or equal to t, this is 0. Z is greater or equal to 0. So it's always true. All right. Now, if I have two random variables z and a random variable w, let's write it this other way. If I have a random variable w and a random variable z, and w is always less than z, then expectation of w is always less than expectation of z. Agreed? Okay. So hence, t times expectation of this random variable is less than expectation of z. Fine. What is this here? What is the expectation of this indicator? Expectation that 1 z greater or equal to t.
That's just the probability that z is larger.
Exactly. That's just the probability that z is greater or equal to t. Okay. And that proves this statement. Okay. All right. So now from Markov, let's go to another statement called Chebyshev. Okay. Chebyshev inequality says the following: let W be a random variable. Okay. Then probability that W minus E of W give me 1 second. Okay, then probability that W minus E minus its expectation is greater than T. That probability is less than variance of W divided by T squared. Okay. What is the proof of this? We just have to apply Markov. Okay. What am I applying Markov to here?
Because we can replace the original z with the variance.
Not with the variance. You are very close. We can replace the original z with W minus E of W squared. Okay. And then apply Markov. Why? Because the variance of W is just E of Z. It's E of this. Okay. Make sense to everybody? So now let's go here. what is the implication for our case? Let's go back. We have this quantity. What is the mean of this quantity? Under x1 through xn fixed, well, it doesn't matter actually. What is the mean of this quantity? It's 0, right? Okay. Fine with everyone? Okay. So the mean of this quantity is 0. And we're just asking whether this quantity minus its mean is greater than epsilon over 2. Okay. So probability that this variance term v of x is greater than epsilon over 2, right, is now, by Chebyshev inequality, it's less than the variance of this quantity, okay, divided by epsilon squared. I'm going to call it eta bar. That's this quantity, eta bar. Okay. This is the variance of eta bar times 4 over epsilon squared. Agreed? And then what did we say that the variance of eta bar was? We say it's like sigma squared over k. So this is like 4 over epsilon times sigma squared over k. Fine. And we now know that this will go to 0 if k goes to infinity. If I go back to this part of the theorem, we had the k go to infinity part. Okay. So we're seeing where the k go to infinity is coming in. Fine. Any question up till here? Everybody following? All right. So let's now go to the bias term. This was f tilde k of x minus f of x. Okay. And same thing, we want to see whether this is less than epsilon over 2. All right. Intuitively, we've already argued that for this to be less than epsilon over 2, for this to be small, it should be somehow that r tilde k of x is small. Okay, because we're going to use continuity here. Recall that the f tilde k intuitively was nothing but this. It was the average of these guys. That's the f tilde k. It's the average of these guys. Okay. And as we said, this average is going to go close to this if r tilde k is getting small. All right. So first, let's write out what these terms are. F tilde k of x minus f of x. Let's write out what it is. 1 over k sum f of xi, I in kn of x. Okay. I can bring in f of x. Fine. Under the summation. Agreed by everybody? So I bring in this under the summation. And so therefore, this thing is just this, okay? And by a triangle inequality, it is at most this thing. Agreed by everybody? And in fact, it is at most the sup x prime in Bx r tilde k of x, f of x prime minus f of x. Everybody sees that?
Sorry, where is this r delta k defined?
R tilde k, r hat k, sorry.
Okay.
Is that what you meant?
Yeah, that's more clear.
Yeah. R hat k, okay? It is almost this thing. Everybody agrees. We're just saying how big can this be? It has just to do with how much f can change in that neighborhood. Okay, that's all it is. It's how much f can change in that neighborhood. Now, this is the point where we know that we've said that f is continuous, right? Okay, so by continuity, there exists Rf of epsilon over 2 such that, and this is the key point, if r hat k of x is less than Rf of epsilon over 2, then this entire thing is less than epsilon over 2. That's just the definition of continuity, right? It just says that for any value of epsilon, if I get close enough, then all the values of f are close to the value of f of x. And this is true no matter what f is, as long as it's continuous at x. Okay?
I have a question.
Go ahead.
Like you said that by triangle inequality, that the f tilde k x minus fx is less than or equal to 1 over k times the sum. But why we wanted a 1 over k to appear here?
Oh, because otherwise there are k terms here, right?
Oh, yeah.
Under the sum, there are k terms. If I don't have the 1 over k, then I have k times this thing.
Oh, right.
Okay.
Thank you.
All right. Fine with everybody so far? Okay. So now I literally just have to show, in other words, I just have to show that r hat k of x goes to 0. If r hat k of x goes to 0, right? Then necessarily for a sample size large enough, I will eventually have that r hat k of x is less than rf of epsilon over 2. Note that epsilon is fixed. And since epsilon is fixed, rf of epsilon over 2 is fixed. F is fixed. Fine? It's just some quantity. We don't know it, but it exists. Okay? Any question?
What is RF?
It's by definition. By continuity, Rf of epsilon over 2 exists. It is that radius such that for, okay, this is the intuition. This is f. Let's say that this is x here. So this is f of x. I'm just saying that by continuity of f, if I want a value, if I want the value of f not to change too much, to change at most by epsilon over 2, all I have to do is look at points in a particular neighborhood, and I'm calling the size of that neighborhood Rf of epsilon over 2.
All right, thank you.
Make sense? That's what continuity gives us. Okay, that such a neighborhood exists. Okay. All right. So we know that such a neighborhood exists. And now we just want to be able to argue, in fact, that all we need is that Rk goes to 0. R hat k goes to 0 with some probability. Okay. Fine with everybody? Okay. So we are almost done, but I just want to first give you an intuition. Okay. I'm going to define something a little more complex to define, but I'll explain it. Right. Okay. First, let's have some intuition. Let mu hat x of x denote, actually, mu hat of x denote the empirical distribution. All we mean by that is if I say mu x of bxr, all I mean is the number of samples xi in bxi divided by n. Bxr divided by n. Okay. That's called the empirical distribution. Following? Okay. So now let's consider that it should be intuitive that this hopefully is close to mu x of bxr. Does that make sense? Does that make sense to everybody? Okay. So it should be close to mu x of bxr. In fact, I can apply Chebyshev to say that it is close to mu x of bxr. Do you see why? Does everybody see that this thing here is just an average? Do you guys see that? That it's just an average? What is it the average of? Okay.
The average of whether each sample is inside Bx.
Exactly, average of that indicator. So it's just 1 over n sum 1 whether xi is in bxr. I1 through n. Okay, so it's just an average. Because it's just an average, the mean E of this thing is exactly this thing. Okay, and so I can apply again Chebyshev to this thing. Fine with everyone? So now, why are we talking about this? Talking about this mu of bxr. Because the hope for us, we're trying to characterize r hat k. The hope for us in characterizing r hat k is that what do we know? Here is the first thing. What do we know about mu hat x What do we know about mu hat x of bx r hat k of x? How many samples are in this ball?
K.
About k samples, right? Fine. So I'll say this is approximately k over n. The only reason I say approximately is that there could be ties. There could be more samples, fine? But it's about k samples, okay? So I should be able to characterize R hat K if I can characterize the ball, the radius of the ball such that I have K over N, such that the mass, the true mass of that ball is K over N. Okay. The intuition is that R hat K of X should be close to the R such that mu X of BXR is approximately K over N. Okay. Fine. And I just need to be able to say that that R goes to 0 as K over N goes to 0. Make sense? Okay. So now define R, what should I call it? Define the following quantity. R of alpha as the inf over this set. It's the set of radius R's such that mu X of BXR is greater or equal to alpha. Okay. In other words, it's the smallest R such that mu X or BXR is at least alpha. So the way to think about it is this. Suppose that this is the entire set of possible x's. This is little x, okay? If I take a ball very large, what is mu x? And let's call this B. What is mu x of B? B is very large. It's contain all possible data points. What is it? Mu x of B is 1. Fine? Okay. And what we want is that if now I'm saying, let mu x of B, let's consider just the ball B, such that the mass here, mu x of B, is just greater than alpha. And if this ball is the ball where mu x of B is greater than alpha, then any other ball greater than it also satisfies mu x of B greater than alpha. Okay, so I'm just going to consider the smallest ball for which mu x of B is greater than alpha. Okay, make sense to everybody? All right. Now, this is a simple fact. We won't prove it. For x in support of mu x, R, in fact, let me call this Rx. Rx of alpha goes to 0 as alpha goes to 0. Okay. That should be somewhat intuitive, right? From what I just did. Does that make sense? If I'm letting alpha smaller and smaller and smaller, that smallest ball containing at least alpha mass will go smaller, will get smaller. Okay. Fine with everyone? Okay. Now, consider, in other words, what we just said is that Rx of K over N goes to 0 as N goes to infinity as long as K over N goes to 0. Okay. So I'm considering that radius that contains the radius of that ball, the smaller radius of a ball that contains about K over N mass. Okay. And I'm saying this goes to 0 as long as K over N goes to 0. All right. Fine. And in particular, I'm going to consider even something bigger. I'm going to consider Rx of 2k over n. Okay, fine. And define R k of x as Rx of 2k over n. Okay. What do we know? What do we know about mu x of b x to Rk of x? What do we know about it? It's greater than what? It should be greater than, by definition, it should be greater than 2k over n, right? 2k over n is my alpha here. Fine. Are you guys still following? I know the proof got a bit complicated, but I hope you're following still. I'm just considering this particular R where we have the mass, the true mass is at least 2k over n. Okay. And if I take, go ahead.
Yeah, so what you have derived is just using, so it's just using your definition, but you replace alpha with 2k over n.
That's all.
Okay.
Okay. I replace alpha with 2k over n, and then I'm looking at 2 times rk. Okay. I'm saying that if I take 2 times rk, I should get this by definition. Okay. Fine. So in other words, I'm considering this ball, the ball that has radius 2 rk of x. Note that 2 rk of x is not a random quantity, right? It exists. The ball 2 rk of x is the ball 2 rk of x contains at least 2k over n points. Okay. Does that make sense?
Can you explain that again? I don't fully understand.
Oh, okay. So what am I doing here? I'm saying let's consider, maybe I shouldn't have removed the drawing. Let's consider a ball around X such that the true mass of that ball, okay, and I'm calling it some ball, I'm just gonna call it 2rk of X, such that the true mass of that ball is greater than 2k over n. 2 times k over n, okay? And I'm going to consider the smallest such ball. So I first started by defining the smallest such ball. Make sense? I just want, don't forget the inf and all that. I think the infs and all that are not easy for everybody to follow. Think about smallest. I want a ball that contains 2k over n mass. Fine? And I'm looking at the smallest such ball. And all I'm saying is that if k over n is a quantity that goes to 0, the radius of this ball would also go down. Okay? Everybody agrees? Okay. So the radius of that ball will also go down. Now, if the radius of that ball goes down, in particular, let k over n small enough, in other words, n large enough, okay, such that rk, 2rk of x is less of x is less than this thing, RF of epsilon over 2. Okay. For sample size large enough, since we say that this thing goes down, there exists a sample size large enough for this to be true. Agree? 2rk of x would become, for the sample size large enough, 2rk of x will become smaller than this quantity. Okay. Now, all that is left is to show what? That r hat k of x is indeed smaller than 2rk of x. Okay. R hat k of x now is a random quantity. Fine. And I just want to argue, if r hat k of x is smaller than 2rk of x, 2rk of x is smaller than rf of epsilon, then from all we did so far, this entire thing is less than epsilon over 2. Make sense? It's a long argument. All right. This entire thing then becomes less than epsilon over 2. Now, how do we argue that r hat k of x is less than 2rk of x? That's all that is left, and we'll do it in 2 minutes. Okay, that's where Chebyshev comes in. I already gave you the intuition of how we're going to argue it. We're going to argue that the mass, the empirical mass of that ball, is not far from its true mass. Okay. So, in particular, suppose that mu hat x of bx to rk of x is greater or equal to k over n, okay, then what can we conclude about r hat k of x? R hat k of x, again, is the radius of the ball containing k points. Okay? If this ball, what is this saying? Mu hat of x bx is greater than k of n just means that this ball here contains at least k points. Okay? It means this ball contains at least k points. If this ball contains at least k point, then that means that the maximum distance to the kth nearest neighbor is less than 2rk of x. Is that reasoning clear? Okay, all right. So I just need to show that this ball contains at least k points, right? And let's look at the probability that it does not. Let mu x bx to rk of x. Let's suppose that mu x bx to rk of x is in fact strictly less than k over n. Okay. That will mean what? That will mean that it is less than mu x of bx to rk of x divided by 2. Okay. Why? Because we say that mu x bx to rk of x is greater than 2k over n. So if this thing is less than k over n, then it is less than the true mass divided by 2. Okay. Fine. This probability is less than the probability that mu hat x bx to rk of x minus mu x bx to rk of x absolute value is greater than mu x bx to rk of x over 2. Do you guys see that? All I'm saying is this: mu hat x less than mu x over 2. Okay. Then it has to be that mu hat x minus mu x is less, mu hat s minus mu x is greater than mu x over 2. Okay. Fine. Just think about it pictorially. Suppose this is mu x, right? Suppose this is mu x over 2. So if mu hat x is here, the distance between mu hat x and mu x is greater than mu x over 2. That's all we're saying. Make sense to everybody? It's again triangle inequalities. Okay. Now, trust me, when I was doing this in my head, it was quick. I didn't realize that doing it step by step like this is actually going to take some time because it's a lot of things to remember. Okay. So, but we are essentially done because this is where we apply Chebyshev. This is a mean. This is an average. This is the it mean. And this is some value t. Okay. Fine. This is exactly of the form probability W minus E of W greater than T. And we say that's less than variance of W over T squared. Okay. So this entire thing is less than what is the W here? It's this guy. Okay. Agreed, everybody? This is the W. And so this is less than variance of mu hat x bx to rk of x over mu x bx to rk of x divided by 2. I have a 4 here. I have a square here. Okay. Fine. Now, to conclude is not immediate. Let's conclude. What is variance of this? Let's go back.
The sigma?
No, sigma doesn't come in anymore, right? I have the mu hat. The mu hat is what? It's the number of samples divided by n. It is this divided by n. Okay. So what is this here? What is this part here? What type of random variable is this random variable? A Bernoulli. Everybody remembers? It's a Bernoulli random variable. It takes value 1 and 0. Fine. What is the probability that it takes value 1? The probability that this random variable takes value 1 is just this. It's the mass of this ball. It is the probability that xi falls in the ball. By definition, that's what we mean by the mass of the ball. Okay. This is the probability. The probability that this is 1 is exactly the probability that xi is in the ball. It is the probability that it is the mass of the ball. Okay. The Bernoulli, so this will be variance of 1 xi in the ball, this ball, divided by n times mu squared x bx to rk of x. Okay. Now, it turns out that the manipulation is actually quick. It turns out that the variance of 1 over x is just mu x, the same mu x, times 1 minus mu x. Okay. The variance of a Bernoulli is p times 1 minus p. Bernoulli p has variance p times 1 minus p. Okay. So the variance of this indicator, which is a Bernoulli, is just mu x times 1 minus mu x. All right. So I have mu x cancel with mu x. 1 minus mu x is bounded by 1. So let me just conclude here. This entire thing is bounded by 1 over n times 1 over mu x of bx to rk of x. And this mu x of bx to rk of x, we say this is greater than k over n, than 2k over n. Okay. I had the 4 here. This is greater than 2k over n. So if I bring that in, right, I have 4 over n times 1 over 2k over n. So I have 2 over k, essentially. Fine? Fine with everybody? Okay. And then this, what is this? This goes to 0 as k goes to infinity. Okay. Now the parts that you might not, technically we are done. The proof is finished. Okay. But I'd like you to see why it's finished. Let me just go quickly over. The main reason why is here. Okay. What we've just shown is that the probability that r hat k of x is not less than 2rk of x, that probability is at most 2 over k. Okay. In other words, the probability that r hat k of x is less than 2rk of x is greater than 1 minus 2 over k. Fine? Okay. The only way, moreover, the only way that, now going back, the only way that the bias term is not below epsilon over 2, right? That's the sequence of events. The only way this is not below epsilon over 2 is if r hat k of x is greater than 2rk of x. And we're saying that the probability of that is less than 2 over k. Okay. In other words, what we showed, is that probability f tilde k of x minus f of x greater than epsilon over 2, that probability is less than the probability that r hat k of x is greater than what we define as rk of x, 2rk of x. Okay? Because we say that if r hat k of x is less than 2rk of x, okay, and rk of x is less than, so why? If r hat k of x is less than 2rk of x, which is less than rf of epsilon over 2, then f tilde k of x minus f of x is less than epsilon over 2. Okay. This statement implies this statement. And we say that this thing, this probability itself is less than 2 over k. Okay. Now, if I go all the way back, recall this part, all I had to show was that the probability that Vx is greater than epsilon over 2 is small, and the probability that Bx is greater than epsilon over 2 is small. The first thing we did was to show this, okay? And then the last thing we did was to show this. Fine. What we showed is that this probability here is less than 2 over k, okay? This one here, it is less than approximately 1 over epsilon squared, 1 over k. Okay? These two things go to 0 as k goes to infinity. All right? And this is also provided that k over n goes to 0. And that concludes the proof. All right? We went over time, but we can still take a couple minutes to clarify anything that people haven't understood, and also ask any more general questions since this is the last time that some of you guys would have seen me, unless you come to grad school at Columbia, okay? Or I see you at some conference somewhere in the future. All right, so we'll stop here. And what we've seen is really just this basic fact. So now you sort of understand why I said there is no time to prove the more general facts, since even this baby version takes a little bit of time to think about. Okay, fine. All right, so questions?
Yeah. So I wanna. So would you like to clarify the? I mean, is there a name for general method of proving? I mean, is there a name for the method we use of proving this baby theorem? Because I think like there's something. There's some interesting thoughts in it that like we're proving the the tail bonds for two different things and we combine it together. I mean, is there a? It's
an approach that comes often, right? So often what you have to do in order to show something complicated is break it into small parts. You tell yourself, okay, for this to happen, for this thing to converge, let me divide it into two parts. So intuitively, the two parts in which I divided it were immediately just these two, right? It was intuitive. Why? Because I could say, I'm just averaging the y values. And in fact, in averaging the y values, what I did is, what I'm doing is averaging the f and averaging the noise separately. Okay, so then intuitively I can think about, okay, what is the intuition? I can think about the intuition of whether this thing converges to f and whether this thing converges to 0. So that's the type of step that happens often in even the larger, even the more general theorem has these steps. But it's just that in the more general theorem, there is more ingredients that come in, okay? That come into play. Yeah. But it has these various steps. There is no name for it. It's just that after you do so many of these proofs, your mind quickly goes into what are the components of the quantity you're trying to bound. How do you decompose that quantity? Okay, into smaller parts, and each part you have a control over that part. Does that make sense?
Okay. So, and also I also have a question. And could you generally, like briefly introduce what is the correlation between the baby theorem and log theorem? I mean, the proof strategy. Does the proof strategy similar, or like
It's
they're
very similar. That's why I showed this one.
okay?
It's very similar. The thing here is that I'm considering just a single point X, okay? And in the general one, I need to consider all the points, right? And different things may be happening at all the points. And in the general one also, I didn't assume continuity, right? Give me 1 second, huh? I keep getting random spam calls. And so, yeah. So one of the key things there is that in the general one, we don't assume continuity. So the part of the theorem where I'm using continuity will not work.
Oh, yeah.
Does that make sense?
Yeah.
Okay.
And I have a final question. It's very short. I mean, is Josh Ellman in Columbia now?
Is who?
Josh Ellman.
I have no clue.
Oh, okay. Thank you.
Questions, anybody?
Yes, I would have a question as well. So the very last bound you gave that concluded the proof, that actually allows you to give rates, right? So I can set like epsilon to, I don't know, 1 over n, and then say, how do I have to choose k?
Which very last bound? You mean on the r hat k?
The 1 minus the probability using the probability for the bias and the probability for the variance term.
Do you remember what page that was on?
No.
Not here.
Yes, here actually, exactly. Okay. The second line. So you get a bound that's like 1 minus 1 over exactly. So you could use that to give rates, right? So I don't know.
Yeah, that's a nice question. So one of the things I was hoping to be able to do, literally, I thought I could go through this entire proof yesterday in 30 minutes. But you guys come from a lot of different backgrounds, and so it's best, like I said last time, that I slow down and that everybody understand every step. One of the things I was intending at first was to give you also how do you go from here to getting rates. Okay, so we are in fact very close to getting rates. All right, and however, a first thing is this. If you want to get rate, you need to use a slightly better tail bound than the one I used. I used to get the best possible rates. You can get a rate with this if you want to, okay? However, this is the issue with Chebyshev. The epsilon appears in this rate. However, I want the epsilon itself also to be the rate. So Chebyshev, unfortunately, brings the epsilon and the probability part together. Does that make sense what the difficulty is here?
Yes. My question was then that generally, especially for the bias term, I think some of the bounds.
For the bias term, we are fine. The bounds were nice. 1 over k is sort of not a bad bound, okay, for the probability part, because it didn't bring in the epsilon. All right. In this part, it brought in the epsilon, which is a bit of an issue, because I want to optimize the epsilon and I want to optimize the k at the same time. But I coupled them in this bound. I coupled them too much. Does that make sense? So, in fact, what you have to do here is use a much faster tail bound. So, in fact, if you guys have heard of a Chernoff bound, a Chernoff bound applies here. So I can use a Chernoff bound, which says that, in fact, the probability of this deviation is exponentially fast. The probability of such a deviation, right? If, for instance, I have X bar, which is an average over n samples, minus E of X bar, the probability that this is greater than T behaves more like exponential minus T squared n. Okay. Rather than what this is giving, what Chebyshev is giving me, which is something like 1 over T squared n, right? Okay. So now if I use something this fast, then it will turn out that the variance term, in fact, just behaves like 1 over square root of k. And what I mean by the variance term, that Vx itself, the epsilon itself, can be replaced by 1 over square root of k.
Can I ask a follow-up question on that?
Yeah, go ahead.
Isn't that a bit weird? Because then on the right-hand side of the bound I was pointing on to, there would only be the k and not the n and no epsilon. But that would tell me that I only need...
Which on the right, no.
Yes.
So here, I would say that the probability that this is less than about 1 over k, 1 over square root of k, is bounded in terms, but don't forget the k, I'm going to view the k as a function of n also, eventually.
Yes.
Okay. Will be bounded by about exponential, something exponential in the parameters. All right. And then I will have a variance term that is about 1 over k. So let me just tell you quickly what it is. And then I think that will answer your questions more. So what I'll have is I'll have a variance term that is about 1 over square root k. But I have now to get rate, I need to make some more assumption on the function f. Okay. Because notice here, I'm using this weird quantity Rx of alpha. And I just say Rx of alpha is going to 0. And that was enough because I didn't care about the rate at which it's going to 0. The moment I need to say at what rate it's going to 0, I want a final rate, I need to also have a sense of at what rate is this thing going to 0. Okay. And not only that, more importantly, I have this Rf of epsilon over 2. I also need a sense of at what rate is this going to 0. Make sense? So usually the assumption that people make to get a control on both of those terms is they, for instance, might make the assumption that mu x is uniform on some bounded space, on a compact space in RD. By saying it's uniform, it allows me to get a sense of what the mass of balls BXR is. If it's uniform, then mu x of BXR behaves like R to the D. Okay? Do you guys see why? If I put a uniform mass on a hypercube, on a cube, every part of the cube is R, then the total volume of the cube is about R to the D. Okay? By assuming it's a uniform thing, I get that this is approximately R to the D, and that allows me to say how this quantity behaves. Okay, this quantity Rx of alpha behaves then like alpha 1 over D. Because the mass of this ball is like R to the D, and I want it to be greater than alpha, so R has to be approximately alpha 1 over D. Okay, so what that tells me then is that my KNN radius, R hat K of X can be bounded approximately by K over N, because the alpha is set to K over N 1 over D. Okay, so then I have two terms. I have this thing is bounded by two terms. One of the term is about 1 over square root K. The other term is about K over N 1 over D with high probability. So now this tells me there is a trade-off on the value of K here. When K goes to infinity, this goes to 0. But when K goes to infinity, this goes to infinity. But this is a nice function of K. I can optimize this function of K and get the optimal value of K that gets me a rate.
Yes.
So it's a long answer, but I hope it sort of gives you a sense of how you arrive at a rate.
Yes, that's
okay?
basically what I...
Yeah. And the one thing that is left is really that you need to make an assumption about how truly continuous F is in order to get a sense of what this RF of epsilon is. Okay. You can, if you've heard of Lipschitz functions, Holder functions, things like that, those are the type of assumptions we make. Okay, we can say, for instance, that every derivative of F is bounded. Okay, and then that allows you to say how big this will be. Okay.
Perfect. Thanks a lot.
All right. Other questions? So the one thing I wanted to mention here before you guys go is we talked about universality, and then we also say that universality can be defined in terms of rates. Okay. So here is a beautiful result. It's called a no free lunch theorem. And the no free lunch theorem says the following. It says that give me your favorite algorithm. Okay. And then give me any rate. Then nature can produce a problem such that your favorite algorithm cannot converge that fast. Okay. Does that make sense? I'm just paraphrasing what it says. Give me your favorite algorithm. Give me any rates you like. Then nature can always produce a problem, a function f in this case, such that your f hat can never approximate f as fast at the rate you want. And that means that if universality were to be viewed that strongly, it's not possible. Okay. In other words, it forces us, it's telling us that to do learning, you need to know a little bit about the problem. You cannot have this universal learning algorithm that just does as well as possible on every problem. It's impossible. Okay. All right. It's a couple minutes, but one more question and then we'll stop here. I know that many of you guys want to, I don't know which activities are scheduled, but other questions? All right. So good luck on the rest of the week and have fun. So these various type of questions are there, and they are still being, these are questions that are still being researched. People are still coming up with situations where there is a universal learner, situations where there is no universal learner. In all these cases here, we are dealing with very nice spaces. A Euclidean space is a very nice space. People think about other spaces where there is no Euclidean structure. Maybe there is just a metric on the space. Maybe there's not even a metric. There is just, for those who have taken real analysis, maybe there is just a topology on this on the space. What can we say in those cases? It all gets beautiful yet complicated. Okay, so there is tons out there to be understood still. All right. Okay, so we'll stop here. Thanks a lot for listening, and good luck on the rest of